Happy Tuesday. Welcome back. We've got a couple things to cover from section 11.5 and 11.6. The goal is we're going to keep on pace, and then Thursday is going to be just a review day. So we'll spend the whole day reviewing. I'm working on getting a review guys ready for you. I want to start out with a kind of famous series called Leibniz series. Now let's take a look at this series. Can you kind of see the pattern of what's going on here? What would be, for instance, the next term in Leibniz series? Yeah, 1 over 11, all right? And the general term, if you wanted the general term, is going to be a sub n is going to have a denominator of 2n plus 1. It's just going to be an odd number. The term in the numerator, well, something's make these terms alternate. Now, I think that this case is going to be negative 1 to the n minus 1 will work. So that's going to be the general term here, but let's compare that to the harmonic series. Take a look at the terms. They're not growing all that fast. It's just really kind of like almost a constant multiple of the harmonic series. What do you know about the harmonic series? Does it converge or diverge? Diverges. Good. So diverges. Can anyone give me a quick reason why? Perfect. P series, P equals 1. Nice. So it'd be kind of, reasonable to expect that this would diverge, but it doesn't. And it actually has a really surprising and beautiful answer here. This adds up to pi over 4, which is kind of surprising. It's like, wow, where did that come from? We'll actually figure that out later in this course. But what makes this converge instead of diverge is that these series alternate. They're going positive, negative, and they're getting smaller. These terms are going towards 0. So those two things together make this an alternating series, and it's going to converge. Your alternating series are going to converge as long as they're decreasing. So that's what this thing is here, right? This condition. So they're decreasing, or at least not getting any bigger as you go from one term to the next. So if you got both of these two conditions, that it's never getting any bigger, and its limit is 0, then an alternating series will converge. So this is another test for you. This is the alternating series test. So to use this, you got to take note of a couple things. First of all, your series has to alternate, and it's always non-increasing. And then secondly, your limit has to be 0. So let's see if we can't apply a couple of these things to some series. The first one is right here for example A. And I guess what would help us out is if we understand a few things about alternating series. So let me back up a second here and talk about alternating series. Now here's a couple ways you can have your series alternate. You can put in a term like this, negative 1 to the n. If I put in a 1 here, negative 1 to the first power is negative 1. If I put in a 2, negative 1 squared is positive 1, 3, 4, etc. They alternate. But let's take a look at a couple more here. Let's take a look at this one, for instance. What happens when we put in a 1 here? I get negative 1 to what power? 0. So negative 1 to the 0 power is 1. Then I put in a 2, and I get negative 1, and then a 3, and then a 4, etc. So it has a different alternating pattern. How about the last one? We'll take a look at the last one. So instead of a minus 1 here, I've got a plus 1 here. And there's something kind of interesting that happens here. If I put in a 1, I get negative 1 to the second power, which is 1. Negative 1 to the third power when n equals 2. And what do you see happening? Well, the answer I was hoping for was that these two are the same. So it doesn't matter which of these you use in the exponents. And there's other expressions you can use to make your series alternate, but really only need two of these. Pick your two favorite and make your series alternate. Let's come back down to example A then. One of the things I'm going to need to know is what's the general term in this sequence going to look like. So let's start out, we're going to build up A sub n. And we got to choose one of these that's going to make our series alternate in the proper order. You want to start with a negative. So I'm going to use A sub n, B sub n, or C sub n. What do you want to use? A sub n. Kind of only one choice in this one. So -1 to the n. All right, we've taken care of the alternating part, so we're good there. Now let's work with the actual terms in this series. Let me call this A sub 1, A sub 2, A sub 3, A sub 4, A sub 5. And work with the numerator and denominator parts separately. So in the denominator, well, let's start with the numerator. If you take a look here, we got a 1 here and a 2 here, a 2 and a 4, a 3 and a 6, a 4 and an 8. What is this term in general going to be for A sub n? Take a look at the pattern, or, yeah, 2n. Good, 2n. Now in the denominator, we start with a 7, and then an 8, and then a 9, and then a 10, etc. So it's kind of marching up slowly. But let's see here. You go from a 1 to a 7, a 2 to an 8, a 3 to a 9, a 4 to a 10. Can anyone see a general pattern here involving, our subscript here, the number of our term, and the term in the denominator? N plus 6, right? N plus 6. So there's the general form of your alternating sequence. To decide if this series converges, we need to take a look at the limit of this as n approaches infinity. Now I'm not going to worry about the -1 part. That just makes it an alternating series. What's going to make it converge is if this limit goes to 0. So the limit as n approaches infinity of the absolute value of A sub n is going to be the limit as n approaches infinity of 2n over n plus 6. I'm hoping that you can evaluate that one without necessarily pulling out L'Hopital's rule. What's that limit going to be? 2. And there's kind of a problem with that. That's not equal to 0. So if it's not equal to 0, it's going to diverge. All right? And we could have actually figured that out with the nth term test even before we did this problem. So this one diverges by the alternating series test. You could also put the nth term test there, I suppose. I would accept that. That would be fine. Okay, so we're good on that one. Let's move on to example B here. And let's see, example B. We got the sum from n equals 1 to infinity. Got another alternating series here. We've got 5 times -1 to the n over e to the negative n. I could rewrite that as the sum from n equals 1 to infinity of, let's pull the 5 out in front, -1 to the n over e to the n. It's -1, not an I. let's take a look and see if this thing is going to converge. So the general term in the sequence, well, the general term in the series, but sequence is the list of terms in that series. The general term, a sub n, is going to be 5 times negative 1 to the n over e to the n. Let's take a look and see what happens to that term. Now it is going to alternate. Take a look at the limit as n approaches infinity of the absolute value of a sub n. And I'm only putting the absolute value in there because I want to ignore the alternating part here. I'm really interested in limit as n approaches infinity of 5 over e to the n. What's that limit going to be? Can we just kind of eyeball that one? Yeah, you're going to be dividing 5 by some number that's going to get increasingly large very quickly. So yeah, that limit's going to go to 0. Nice. Now, this one's a little different than our previous one. Our previous one, we didn't need, or excuse me, our previous one, no, sorry. Previous one diverged. But this one, we really don't need the series to alternate in order for this to get convergence. So this one would converge even if the series didn't alternate. In fact, can anyone recognize what this series could be written as? Is there another way I could write that series that might make it a little bit more recognizable? Let's play with that a little bit. So I'll rewrite it as 5 times the sum from n equals 1 to infinity of negative 1 to the n over e to the n, or better yet, 5 times the sum from n equals 1 to infinity of negative 1 over e to the nth power. Is that looking a little bit more recognizable? Well done, James. Thank you, sir. Yeah, geometric series. So it's going to be 5 times negative 1 over e to the first power plus 5 times, let me just do it this way. I'm going to get tired of writing that 5. Yeah, negative 1 over e to the second power plus negative 1 over e to the third power, and so on. So it's a geometric series. We really didn't need it to alternate in order for this to converge. So that's going to be 5 times the sum of a sub 1 over 1 minus r. Remember, that's the sum of a geometric series. Let's fill in a sub 1 and r for this particular geometric series. What's a sub 1 for us in this case? Well, that's the first term. It's going to be negative 1 over e. And then what's r? Yeah, same thing again. So overall, what I'll get is 5 times negative 1 over e over 1 minus 1 over e. Probably want to clean that up a little bit. I would multiply both numerator and denominator by, let's see, we'll do negative e, and negative e. In the numerator, that's going to give me just 1. In the denominator, I'll get negative e plus 1, or better yet, when it's all said and done, 1 over 1 minus e. Okay. Now, this is going to converge to something negative. Yeah, okay, I guess I can kind of buy into that, because as these terms get smaller, the largest term is going to be a negative term. Alicia?
In the denominator, is it supposed to be plus 1 over e? Or is it the absolute value of y?
No. It's a minus 1. 1 minus r here. Oh, wait, you know what? There's going to be a double negative here. You're right. So that double negative is going to be a positive. Let's see. That's going to be the same. This is going to be a minus. Yes. Thank you. And let me factor out the negative. I'll put it up on top and then make everything in the denominator positive. So, cool. There's your summation. Because this series converges, whether or not it alternates, this is called absolutely convergent. So the series is absolutely convergent. And that's because the whole series converges independent of it alternating. Some series, like Leibniz series, only converge because they alternate. That's conditionally convergent. All right, let's try some more. Comments or thoughts on example B here? Okay, let's move to example C. Got the sum from from 1 to infinity of -1 to the n. 1 to the n times sine of 7 pi over n. Okay, well, at least the series alternates, and you can kind of convince yourself a little bit. Let's take a look at two adjacent terms. We'll call this our b sub n, just giving it a different name for a change. B sub n is sine of 7 pi over n. What would b sub n plus 1 look like? Sine of 7 pi over, well, n plus 1, right? You're putting in the next term. Now, how do these things compare to each other? Well, after n equal 8, when these terms start getting bigger than their numerator, it's going to be bigger than the coefficient in the numerator, the sine function is going to start decreasing. So for n greater than or equal to 8, b sub n is going to be greater than b sub n plus 1. So it's decreasing. Sometimes these things are a little bit more obvious than not, but we're checking that first assumption. The second assumption we have to check is this one, the limit as n approaches infinity of b sub n. I'm not going to worry about the negative part, the alternating part. I just want to see that this limit is 0. Limit as n approaches infinity of sine of 7 pi over n. What's going to happen to that limit? Well, I guess because this is a nice continuous function. What we can do is we can interchange our x and y, or interchange our limit and our function. So we can do the sine of the limit as n approaches infinity of 7 pi over n. Somebody help me out with that limit. Yeah, it's going to go to 0. So I'll end up with sine of 0. What's the sine of 0? Sine of 0 going once, twice, 0. Yeah, sine of 0. Cosine of 0 is 1. Yeah. So it's a decreasing sequence, and the limit is 0. So therefore, the series converges by the alternating series test, which thankfully I'll let you abbreviate that as AST. Let's move down to some more examples. I think I'm going to skip example D. Yeah, please.
Why did you choose sine 7 pi over n for these?
Because that's the meat of this series. I mean, this is just the term that makes the series alternate, but this is going to converge if this part of it, the part that's not alternating, if this part of it goes to 0 and it's decreasing, generally speaking, then by the alternating series test, we've met those two criteria. Those two are true, so it would converge by the alternating series test. Yeah, no, I appreciate that. Thanks for the question, Brandon. This one is pretty cool, and if I remember right, it's going to end up having a limit that deals with E, but I want to discuss this one when we do the ratio test, so I'm going to hold off on that one. We're going to move on to this one right here. So let's take a look at that. So I'll skip to example E. So we've got 1 over the square root of 3 minus 1 over the square root of 4 plus 1 over the square root of 5, etc. First thing we need to do is probably find a general term for this series. So what would the general term be? This is our a sub 1, a sub 2, a sub 3, a sub 4. I want a sub n. What's that general term going to look like? Okay, so let's start out with the alternating part. What exponent do I want to use here? Go ahead, James.
N plus 1.
Oh, okay. All right, Clyde. Yeah, -1 to the n plus 1. All right, and now let's deal with the fractions. I'll take the numerator for you. There's a 1. How about the denominators? I think somebody already said it. What's in the denominator? Yeah, n plus 2 or 2 plus n. Either way you want to say it, we're in good shape. So there's your general term. Now in this one, it's pretty clear that as you increase the n, this ratio is going to get smaller. So we got kind of this first part here just by looking at it. But the second part, let's take a look at that. So the limit as b approaches, or excuse me, not as b, how about n? As n approaches infinity of 1 over square root of n plus 2. I'm not going to make you do anything fancy with that one. I think we can just eyeball this one. What do we get for this limit? 0. So therefore, the series converges by the alternating series test. Let's see if it converges absolutely. What if I tried to take the absolute value of this series? Does the series converge absolutely? So that would mean, does this series converge? 1 over square root of n plus 2, n equals 1 to infinity. Well, let's take a look at our let's do a gut check first. What does this series kind of look like? Yeah, it kind of looks like a p-series. Kind of ignore the 2 for a minute. We did this the other day. You know, that 2, when your values of n get really, really large, that 2 is not going to mean much. So this is going to be approximately sum from n equals 1 to infinity of 1 over the square root of n. And I think somebody already said it. What's this going to behave like? This is a p-series, right? P-series with n equal 1/2. N equal 1/2, is that going to converge or diverge? Diverge. Now, this series is different than this one. So you either have to do a direct comparison test or a limit comparison test to finish this off. But I think you can kind of see here that these two are going to work about the same. I would use the limit comparison test. That way you don't have to fuss around with, do the inequalities line up in the right direction? Because I think this one is going to be smaller than this one. The fact that this diverges doesn't help you out with this one. So I would use the limit comparison test to finish this off. So by the limit comparison test, this series is not going to converge. And I'm not showing that work here because I want to spend more time with the alternating series. Series n equals 1 to infinity of 1 over the square root of n plus 2 diverges so the overall series that we started with, sum from n equals 1 to infinity, negative 1 to the, do I want n plus 1 here, square root of n plus 2 converges conditionally. Meaning it only converges because it's an alternating series. If it wasn't an alternating series, it wouldn't converge. Leibniz series is another conditionally convergent series. We get convergence in that series because it's alternating.
Professor Kern,
Yeah.
how do you get it to converge if when you take the limit you don't even take into account the fact that it's an alternating series?
It's the certain. So, what's happening is that if you look at the sequence of partial sums, you know, because these things are alternating, you've got 1 over the square root of 3, which is like about 0.57, and then you subtract a little bit, and then you'll add a little bit. But those totals are going to keep canceling each other out to a smaller and smaller extent, and so the sum of the differences starts to get really, really small. I mean, when you start adding this little bit and then subtracting this little bit, these almost cancel each other out completely. So they're like annihilating each other, and these pairs of sums that you're adding eventually get really, really small. They're getting close to 0. So
I guess I'm asking, how, when you do one test, you get convergent, and the other one, you get
Right.
divergent, but in the convergent one, you don't even take into account the fact that it's alternating series.
Well, if we're looking for absolute convergence, then we're looking for whether or not the series converges without it being an alternating series. So here we're just looking at this without the -1 to the n plus 1 part. And if it converges here, then it converges absolutely. If the only reason it converges is because the signs alternate and the limit is 0, then you get conditional convergence by the AST. So let's think here. Trying to think. I'm not sure of answering you. I think I understand what you're getting at here. Let me give this another shot here for just a second. So I think what's bothering you is that, oh, gee, we looked and the limit is 0, and all of a sudden this is convergent. Why can't we say the same thing here? It might be a little bit of what's bothering you. For instance, if all we did was we looked at the limit of this term, in fact, let's apply the nth term test to this. Let's see what the nth term test. So just to kind of follow up on your question a little bit more, n equals 1 to infinity of 1 over the square root of n plus 2. Let's apply the nth term test and see what that says. For the nth term test, we're going to take a look at the limit as n approaches infinity of 1 over the square root of n plus 2. What's that limit? Still 0, right? But what does the nth term test tell you about this series? Inconclusive. Remember, the nth term test doesn't have a conclusion if the limit is 0. If the limit is not 0, it says it diverges. But if the limit is 0, it's inconclusive. So the nth term test is inconclusive here. But if you take into account the nth term test, or this limit, and the fact that it alternates, putting those two together by the alternating series test says, yes, it does converge. So it's more than just that the limit is 0. You have to have that alternating part to make it convergent. It's not enough just that the limit is 0.
So you just ignore it because it's built into the test already?
Yeah, that part is built into the test. I mean, you're applying the alternating series test. I mean, really, there's not much difference between the alternating series test and the nth term test, right? You're looking at the limit as n approaches infinity of each term. You want to see that that goes to 0. But in the case of the nth term test, if it goes to 0, that's where you stop. You're like, okay, there's nothing more I can conclude. But with the nth term test, because they're alternating, you can apply the nth, not because of the nth term test, because of the alternating series test, because they're alternating and this limit is 0, that's what gives you convergence. Is that better? Yeah. Okay. Appreciate the question. Thanks for sticking with me on that one. All right. Let's take a look at, let's see if I can figure out something with Google Sheets here real quick in terms of the sum of a bunch of these terms. Kind of take a look at what's going on. Let's see, Google Sheets. Do a blank sheet here. Let's list out a few terms. So 1, 2, 3 equals here plus 1. And let's just drag this down a little ways. All right, so I've got a few terms. I want each term to equal -1 to the this term raised to that term plus 1 divided by the square root of that term. And then it says, do you want me to fill this all the way down? Sure. And what I want to do is I want to start adding these terms together to see what happens when we start doing a sequence of partial sums. So I'll start right here. I'll add the first two terms together. I'll add this one plus this one. Didn't like that. What was wrong with that? Oh. That's not how I want to do it. I want to keep on adding in each new term here to this sum. So to get this one equals, let's see, I want to do this one plus this one. All right, there we go. And let's see what happens as we keep on adding these terms down. No, I'm not getting the convergence that I wanted to. Yeah, it's starting to get convergence. So what's happening with these terms? If you take a look at these pairs, we got 0.74 and 0.47, and then 0.73 and 0.48. As you add a little bit and then subtract a little bit and add a little bit and subtract a little bit, as these terms get smaller and smaller, you're bouncing up and down between smaller and smaller numbers. Eventually, these terms are getting closer and closer together. Take a look at them here. Instead of 0.7 something and 0.4 something, now they're 0.67 and 0.53. They're going to continue to get closer because these pairs of numbers that you're adding together almost cancel each other out. And as n gets larger and larger, they are going to continue to cancel each other out, and eventually you'll end up with some limit. Now, calculating that limit can be much more of a challenge than just saying that it exists. Yes?
Can you think of it like a graph that's oscillating?
Yes.
And the y values just are getting closer and closer to a certain
That's
number?
exactly what's going on here. Let's do one last thing with this and kind of send it to bed. Let me copy those, paste them over here, and then I want to copy these and do likewise. Oops, no, I don't want that. Paste special, values only. Let's paste these into, I don't know, my favorite program. Anyone want to fill in the blanks? Desmos, yeah. Let's paste them into Desmos and plot them. So there you go. And you can see exactly what's happening. Those are, they're kind of bouncing up and down, but what's happening to them overall? What does it look like they're going to? Looks like they're going to some kind of middle number here, around 0.6, right? So, yay. That's kind of a nice, cool visual. I like it. I don't know. You guys like it? Yeah? All right. Hannah?
I liked it. Oh, no, I liked it.
You liked it? Oh, okay. Appreciate it. Thanks. Bonus points. All right. All right. And minus points for Kaiser because he didn't like it. All right. Well done. Well done. Yeah, so that was actually pretty cool. I'm glad we did that. That's kind of a nice little visual. All right. Let's keep going. So what you're looking at is the so-called sequence of partial sums. And we had some notation for that the other day. That was S sub n. S sub n equals the sum of the first n terms. And that's what I plotted. And you can see that that sum is kind of settling down near some limit. And there's something really cool and amazing about alternating series, and that is the error that you make is going to be the difference between the series itself and, where you cut off your approximation. So if we're going to approximate the sum of this series by, say, the sum of the first 10 terms, how much of an error are we making? Well, the nice thing about an alternating series is that there's a bound for how much of an error you're making. And it's basically the bound on your error, and this is your error in approximating a series with the sum of the first n terms. That's exactly what you're calculating here. I don't know if you caught this in here or not, but S is just the sum of that series. S sub n is recognizing that we're finite creatures. We can't always add up an infinite number of terms in a series. So the best we can do sometimes is approximate it with the sum of the first n terms. And when we do that, our approximation, the error that we're going to make, or the remainder that we get, is going to be less than the first term that we leave off. So that's this term right here. That error will be less, or will be at most the first term we leave off. At most, the first term left off of the series. That's really cool. That leads to some amazing results. Let's take a look at example G here, for instance. And then we'll show you maybe one of those kind of amazing results in a minute. It says approximate the sum of the below series to within 1/10,000th. Says note you can determine the correct term to leave off by trial and error with the table function of your graphing calculator. So, all right, let's bust out some graphing calculators and do a little graphing calculator work. I'm not sure if it's worth it to put it in sequence mode or not. Let's go with not for the time being. Don't think we need to do that. Now the size of this term, what they're talking about really is the size of the absolute value of that term. We're not really worried about the alternating part. So let's just put in the function n squared over 6 to the n into our calculator, into the equation editor part of it. So y equals, let's clear out the stuff here. And then in the numerator, instead of an n, I'm going to use an x because I didn't take the time to put this in sequential mode. X squared over 6 to the x. And we want to decide, well, how many terms do I need to go out before this is finally less than 1/10,000th? Now let's keep a note on 1/10,000th for just a minute. Your calculator typically won't display 1/10,000. 1/10,000 is 0.0001, but on your calculator it's going to be 1e negative 4. That's on your TI-84. So that's really a number in scientific notation. We want to work until we get a number that's less than this. So let's go to our table function. Second. Let's see, second, and then window. Make sure that your table function is set up this way. So you hit the second key and then the window key. Independent should be set to ask. Dependent should be set to auto. Once you have that set, then you can go to your table, second, and then graph. Let's delete all these values here. And you want to start marching up from 1, 2, 3, 4, etc. Yeah. This is a bummer. Well, maybe not. 4, 5, 6, 7. 7. We're close at 7, aren't we? 1.8e negative 4. That's still a little bit more than 1.0 e negative 4. So let's try 8. There you go. Now you've got 4 leading zeros and then a 3, 8. That's what this number represents. So you need to go to the 8th term before your terms that you're adding in are less than 1/10,000th. So to get this accurate to the nearest 10,000th, you would use 7 terms. So the first 7 terms, when you add it up, will give you the sum of this series to within 1/10,000th. So nice. So by trial and error, use S sub 7. Well, let's see if we can't figure out what S sub 7 is. Can you guys stand some more cute and dirty calculator tricks? All right. Let's go to list. And then over to math. So list and then math. And I want the sum. Oops, I don't want it here. I need to exit out of here, sorry. Let me start this again. So second, list, over to math, and then choose sum. Sum of, well, I need a list or a series. So I'm going to go back to list again. This time I want to go down to sequence. And sequence should be menu driven. What expression are you going to use? Well, we need to type in the expression that we have for our terms right here. Negative 1 to the n minus 1 times n squared over 6 to the n. Now, you can type that in with n's if you want. I'm going to type it in with x's. You got to be careful about the parentheses that you're going to use here. So I'm going to do this. No, it's not letting me do that. It's not letting me get any fancy fraction work here. So I guess I'll skip that. Negative 1 has to be in parentheses, raised to the parentheses n minus 1. So I'll do x minus 1. And then times, which I don't really need to hit the times key. I'll just do x squared here, and then divided by 6 raised to the x. So there's our expression. It's asking us for how we do the, or what our variable is. And our variable in this case is a 1, or excuse me, is an x. Our start is at a 1. Where do I want to end? 7. Basically, I'm going to sum up the first 7 of these terms. Our step is going to be 1, meaning I want to go from x equal 1 to x equal 2 to x equal 3. You can do different steps depending on what you need, and then paste that in. I'm going to put another right parenthesis there. Let me show you what's at the start of this line. If you need a quick way to get back to the start of the line rather than hitting, the left arrow key endlessly, hit the second key, then the left arrow key. That'll jump you back to the start. So it's going to sum up this sequence. And there you go. Nice. If you wanted just to see that sequence and then maybe sum it up, let me just get rid of that sum part in the beginning. let's just look at the sequence itself. So there's that sequence. It's not liking that. It's probably because I have unbalanced parentheses. There's the sequence itself. And you can clean that up a little bit if you want to hit the math key and then answer a fraction. So there's the terms in those sequences. You can add that up by hand if you wanted to or needed to, but I choose not to. Once you have this sequence, then you can sum that up if you want to. So you can do second list, and then go to math, down to sum the previous answer. So there you go. You're getting the same thing again. All right, our total sum was 0.0875, we'll call it. Nice. Nice. And you can go as far as you want. Personally, if I did ask you to do something like this on an exam, I'd make the number of terms shorter. That way you don't have to do all this fancy stuff if you don't want to. I don't want to make this course about using the graphing calculator. It is a nice tool. I just want you to know the calculus involved here. Okay, we did a lot on that one. Comments or questions on any of that stuff in G? Was the calculator trick a good one? A or an A? Got thumbs up? Oh, even thumbs up from Kaiser. All right, that's a mark of success there. Good deal. All right. Let's do one last one. Before we do one last one, let me show you kind of one of the applications of some of this kind of stuff. And it's more in line with kind of where we're going in this course. And it's just remarkable that we can do this kind of stuff. Suppose you had to take and find a very common integral, e to the negative x squared. Now, where do they use it? They use this in statistics all the time. You have to find this area all the time. Of course, we've got tons of charts and computers that have done this for years. But here's one way you could do it. E to the negative x squared can be replaced by this infinite series polynomial. All right, that's pretty cool. That's what we're going to be doing soon enough. We're going to work with power series and Taylor series. Now, the nice thing about this polynomial is that you can integrate it. Integrating polynomials is pretty easy, right? You just add 1 to the exponent, divide by that same exponent. So I'll replace this top integral here with this one down here. I'll integrate that and then put in my limits. Of course, at 0, I'm going to get nothing. So it's really just putting in the upper limit. But take a look at this series. What do you notice about that series? It's alternating, right? So that means the error that I make in the approximation is less than the first term I leave off. I'll tell you what, this term, 1/10 to the 5th power divided by 10, that's like 1 over 10 to the 6th power. That's a pretty big number, meaning the error is going to be really small if I drop off everything except the first 2 terms. So if I keep just the first 2 terms and add them up, I get 0.099667, etc., which is really, really accurate. It's just hilarious that you can get such accuracy with just 2 fractions, 2 simple fractions. Give me, 6 digits of accuracy for this integral. So that's where we're headed. And that's why we're taking time to look at alternating series, because it's a nice way to approximate things. So let's do one last one here. Example H. And the big thing with example H is you're going to have to learn or relearn where to find the factorial. So we want to approximate this series correct to 4 decimal places. Another way to say that is to within the 10,000th. Within 0.0001. So I want it to be at least that accurate. So let's do a couple things here. let's put that into our calculator. Let me clear out all this other stuff. Go to y equals, clear that out. And I'll put in -1 to the n. Somehow I'm not sure I really need to bother with that -1 part. Except where an n is, I'm going to use an x. And then in the denominator, 2 to the x. And then x factorial. Now that factorial is what you're going to need help with, or at least I'm guessing a lot of people might need help with. So let me make sure everyone's ready for this little piece here to find the factorial. We're good? All up there? So go to the math key, and then you want to go over to probability, the probability menu. I think you'll see it there. Personally, I'm just going to go to the left 2. You can go to the right 3. The fourth option down is your factorial. Bam. So there's your factorial. Factorial is a number that grows really big, really fast. I mean, 6 factorial is already 720, 7 factorial is 5,040, 8 factorials over in the 40,000s. So it grows really big, really fast. Let's take a look at our terms here. So go up to our table, and can you look at our table and decide at what term, you know, this is finally less than 1 over 10,000?
X equals 6.
Yeah, x equals 6 looks pretty good. At x equals 5, your denominator isn't quite bigger than 10,000th, meaning your error isn't less than 1/10,000th. So we can go to x equals 6. That's the first term that's less than 1/10,000th. So am I going to include that term, or am I going to leave that term off? That's the first one we leave off. So we'll actually use the first 5 terms to approximate that. So we can approximate with S sub 5, that is the first 5 terms. Do you want me to go over doing it again on the calculator, getting those terms to print out and then summing them up? All right, let's do that, and that'll be it for this section. So let me exit out of all this. And if you want to try and follow along, get ready, because here we go. So first of all, let's just create the sequence, the list of those first 5 terms, just to see it. So for that, if I just want to see my sequence, then I'm going to go to the list command, so second, and then the stat key, then to the right one to list. The 5th operation down is to build a sequence. So let's build up our sequence. I'm going to leave some of this here. I'm going to get rid of the -1 in the exponent. And then I'm going to divide that by a product of 2 things. So because this is giving me a sideways fraction, I have to use parentheses in the denominator. It's going to be 2 raised to the x. And I'm going to put a times in here just because I like it visually. I don't think you need one, but I am going to put a times in there. Times x factorial. So let's remind ourselves on the factorial. It's going to be the math key, then the probability key, then the 4th option down, close that parenthesis. I think we're pretty good from there. We want the first 5 terms. You can do the first 6 terms if you want to see that term that you're leaving off, but we don't really want to sum up that term, so I'm not going to put it in there. When you get all these things done, you should be able to go down to the last step there and paste that into your home equation or home screen. Now this isn't very fun to look at it like this, so I'm going to hit the math key, and there you go. That's a better looking set of fractions. If you want to sum that up now, let's go back to our list command here. So let me clear this out. You can keep up with our keystrokes on the bottom here. Second list. This time I want to go over to math, and the fifth operation down is to sum up a sequence. And I want to sum up the previous answer. So I'll hit the second key, then the opposite key, and that's going to sum up the previous answer. Ooh, wow. And you get a nice fraction there too. Gina, missed a key someplace?
Yeah. I can
Did,
just watch
did
it.
you get the fraction?
Yes.
Fractions? So to get this sum, you're going to go back to second and then list. This time you want to go over to math, and this the fifth operation down. That's what gives you the sum. And I just did the sum of the previous answer. So that does it. Nice. Nice. Anything else on this one? Let's see. How did we end up with? Let's see. I actually want a decimal value here, just out of curiosity. So the sum S5 was negative 1511 over 3840. If you want to make it give you a decimal, go back to the math key, and the second operation there, well, actually says, okay, you just want a decimal, there it is. So approximately negative 0.3935. Nice, nice. Okay, that'll do it for section 11.5.